Test. Here we go. So the first thing we're going to do is we're going to talk about something called kinematics. Kinematics, which is the term we give to the study of, I'm going to just put here, how things move. Okay, that's where we're going to start. After that, our next sort of unit will be something called dynamics. I'll just mention it now, which is more why things move or what makes them move. And together, these two things form one big sort of physics unity thing called mechanics. So that's technically what it is that we are studying, mechanics, which is not really fixing cars, but simply studying how things move and why they move and what makes them move. So our first unit, our first little sort of unit will be this, kinematics. Okay? So that's what we'll start with. So if we were to start with kinematics and talking about how things move, we would see some very familiar words or terms show up. Well, if you were to imagine something rolling along or moving along, you could talk about the distance that it travels. So distance, right? Distance is a thing you could measure. You might also measure how fast it actually moves, so speed. You might also consider if it doesn't go nice and steady, maybe it speeds up and slows down. So there might be, an acceleration. And of course, all of these things would happen in certain amounts of time. So we have these four sort of concepts that at first seem extremely simple and straightforward. But as we'll see in a minute, they're not quite that simple, and there's a lot of confusion that we have to clear up right off the bat. Okay? If I were to, say, okay, a distance, 6 miles, 12 kilometers, whatever it would be, it's basically just a number that tells us how many kilometers there are. It's an amount. But that's not good enough for describing the way things move. Because think about if you were sort of here in this classroom and somebody said, I want to go to the mall. How do I get to the mall? So let's say over here is the mall. And you figure, well, you say to them, it's 3.5 kilometers to the mall. Obviously something is missing, right? So here, just look where you are right now. Go to the mall, 3.5 kilometers. The obvious question you're going to ask is, which way? Yeah, what direction? So what you have to do is you have to say 3 kilometers, but you have to add in a direction. You have to say something like east or west or over there. Even if you point, at least you're showing the direction, right? And so typical numbers that we are used to, like 3.5 kilometers, they don't show us anything about direction. This number alone doesn't tell us anything about which way we're going. So what that basically means is we need a whole new kind of number. So if we're looking for a new kind of number that can express both direction and amount, then we need to consider what we call a vector. So I'm going to put vector over here, and we're going to compare it to the numbers that we are used to, which are just amounts. Those have a name too. They're called scalars. So a scalar is just an amount. And there's a fancy word for amount that we use. That fancy word is magnitude. We use that in English sometimes too, the magnitude of something represents how big it is. So magnitude. And if you're a vector, you have a magnitude also, but you also must have magnitude, that's an I. You must also have a direction. So it's a fairly straightforward concept. So let's do some examples. If I were to write 6 kilograms here, That's an amount, right? 6 kilograms. If I were to write 12 meters, that's another amount. I could write 8 pounds, or lbs. I could write 60 kilometers an hour if I was driving on the road. These are all amounts, so these are all scalars. But if we add a direction to them, we could make a vector. Except some things don't make sense with direction. What would 6 kilograms up mean? Doesn't really make sense. So some things, like kilograms, mass, they can't be vectors because adding a direction to them doesn't make sense. So they can only be scalars. But 12 meters can be an amount of distance, but you could add to it 12 meters, and you might say east. And what we do is we usually put the direction part in little square brackets, like this, or big square brackets, to distinguish it from the other part of the number. So there's the two parts of the number. There's the first part, which is the magnitude, and the second part, which is the direction part. Now right now, we're using English words to describe our directions, right? But eventually we will learn how to translate them into mathematical symbols and things. 8 pounds also cannot really be a vector because you can't have a direction for how much something weighs. It doesn't make sense, right? But 60 kilometers an hour could be a vector if you added a direction. You might say up. And of course, the reason we don't like to use English is because there are so many words we could use for direction. Up, down, in, out, left, right, hither, yonder, here, there, east, west, north, south. It gets really crazy. What we want to do is find a way to represent these mathematically that's far simpler and more concise. So that's really the only thing that a vector is. It's a special number that has two personalities, a magnitude and a direction. So now that we know that, let's look at the four things that we talked about already. Let's look at speed. Let's look at the scalar name and the vector name for the things that we just talked about. Let's make a little chart here. Well, we talked about a distance, is how far you go. But if you add a direction to a distance, it becomes a vector. It's no longer 2 meters, it's 2 meters down. So we need a new name to describe it. So they come up with the name displacement. Displacement is a distance with a direction. It's the vector cousin of distance. Get it? Pretty straightforward. And then if you think about speed, well, if you add a direction to 60 kilometers an hour, like we did, we have to give it a new name, so we call it velocity. Now, unfortunately, in English, we often use these two words to mean the same thing, right? Somebody say, wow, that car's got a really high speed. But someone else might say, that car is moving with a rather high velocity, right? And we think that means the same thing, but it doesn't in physics. If we use the word velocity, we specifically mean the part that has a direction along with it. But what makes it harder is that in physics we often just kind of understand what we're talking about. So imagine you and a friend were at this party and there was some big drama happened and it was all crazy, and 2 days later you're at a coffee shop and you're like, hey, remember the party when Sarah was there? And the other person would say, oh, yeah. Because there's no need for you to tell them all about it. They know what you're talking about, right? And so sometimes when we're discussing things as physicists, we sort of all know what we're talking about. We know that there's always going to be directions, no matter what. And so we often are talking about these things, but we use these words. We might say the speed of something, but everybody understands, yeah, but that's speed. Don't forget there's also direction. So that can make it confusing when you're talking. You might see that we're using these words interchangeably, but they're not actually interchangeable. So here's the trick. How do you get around it? You simply remember that everything could be a vector, no matter what you call it. So that means you must always consider direction. Even if you're not, you might consider it and then say, you know what, I don't need to worry about it. That's fine. You can do that. You might be dealing with kilograms and say, there's no direction there. That doesn't matter, and don't worry about it. But you should always, in the back of your mind, think about whether a direction might be important in any kind of situation or anything that you're measuring. So you kind of assume everything might be a vector, and you make a conscious decision whether or not you're going to treat it like one or not. That's kind of the safest way to do it. And in fact, because we use these words interchangeably, we stopped making new names for things. In fact, if you talk about acceleration, you can say acceleration as the magnitude and it being a scalar, but we didn't come up with a new word. As a vector, it's still called acceleration, right? Because even if you don't mention the direction, there still has to be one. If I look at a door and I say, how high is it? You say it's 2 meters. We all understand it's 2 meters up from the ground, right? You don't have to say that. So technically, that's still a vector. So you can see how it can be a little bit confusing when you're first trying to understand all these words. When we use them interchangeably, and we don't make a lot of effort to point out their differences. All right? The other interesting one is time. If you think about time, you say, well, an amount of time, 2 hours, 10 seconds, 35 minutes. It sounds like a scalar. And we often treat it like a scalar, but if you think about it, time does have a direction, doesn't it? Time always goes forward. It just happens to only have, it always goes in the same direction. It's like a car on a road that never turns. Time is a vector that always goes forward. Why doesn't time go backwards? Well, maybe it can. We just haven't noticed that yet. But just because we haven't noticed something doesn't mean that it isn't actually possible, right? And that's an important thing to remember. So time is actually a vector with a direction that never changes. And since it never changes, why bother talking about it? Why point it out? Why waste time? Everybody knows, so we just all understand. And we often treat it like a scalar without worrying about the direction for time. Okay? So that's vectors in a nutshell, and we'll see more about that later. We need to also understand one other very important tool that we will use besides these new numbers, and that is the reference frame. A reference frame is basically a stage on which events will play out. A stage on which events will play out. Okay? So what I want you to do is I want you to imagine, you can't see anything I demonstrate, but if I take a ball and I put it on this stick, we can imagine what's going to happen. So what we'll do is we'll draw a picture here in case you can't see me. Here's a little stick, and the stick is going to be like this, and it has a little groove in the top. Right? And I'm going to take a little red little ball here, and I'm going to put the ball and rest it right in the groove on the top of the stick. And so if the ball is going to move, obviously the ball is either going to go this way or it's going to go this way. And that's going to be it. The ball's not going to be able to go anywhere else. So if you were looking at this ball and you were standing on the side that you're on, you would say that this side is right and this side is left. But if you were standing on the other side of the ball, looking out of the board towards where you are now, you would say this is right and this is left. So you would have two different perspectives. And of course, in order to discuss something, everybody has to agree. Everyone has to agree on what kind of reference frame we're going to use in order for us to discuss the situation. So the reference frame is like setting the stage before you begin to discuss something, you set the stage by determining what kind of reference frame you're going to use. Okay. So now what we'll do is we'll talk about some of the different reference frames that you can get. Well, if we go back to our picture of the ball on the little stick, moving back and forth, the ball in the first scenario has one choice to make. One choice to make. Okay, so this ball basically has one choice to make. So let's move this down a bit. If the ball has only one choice to make, we call that a one-dimensional reference frame. One-dimensional reference frame. So it's a kind of a stage where the only way you can move is like left or right. Like as if you were stuck on that stick, going back and forth, just like the ball. It'd be a very boring play to watch, but some things do move that way. So they have one choice. Right? Of course, if you have one choice, we say there are two options. And that's what you're going to choose from. You're going to choose one of the two options, one choice to make. So that choice, for the case of the ball, might be left or right. It could be anything. It could be up or down, right? It could be in or out. There's lots of different sort of one-choice words that we could use. Back and forth, hither and yonder, or whatever. There's lots of ways to describe that in English. But that's a one-dimensional reference frame. Now, what kind of a shape does it look like? If you have the ball, let me just simplify this by drawing a little thing here. There's the stick, and here's the ball. Well, this ball can go this way or that way, right? I could do this, and if I had a little ball, well, then it would have to go up or down. It doesn't matter which way I draw it. There's still only one choice to make, right? What shape does this look like? What would you call that black thing? It's a line. So one-dimensional reference frames basically are lines. We say that they are linear. So anything that moves in a line can be described using a one-dimensional stage or a one-dimensional reference frame. So the line will become the stage on which we play out anything that moves one-dimensionally. So the ball was a good example on the stick, but in real life, I can think of things like here's an elevator. Well, elevators pretty much go up or they go down. I guess now they have some really fancy ones now that kind of go sideways and do weird things, but a traditional elevator is a one-dimensional thing, right? One choice, up or down. Its motion looks like a line. If you were going to run the 100-meter dash, you would start at the starting line and you would run straight to the finish line. 100-meter dash. Your motion would be linear. Of course, we couldn't include the 400-meter dash because if you run the 400, you're in a line, but then suddenly you have to go around the track and curve. And that's not a line anymore, that's something else, totally weird. So we won't even put that on there. Only the 100-meter dash is a straight line, right? You could imagine a train. A train on a track, right? As long as the track is straight, the train can only go backwards and forwards. It can't go anywhere else. That could be a linear reference frame. Makes sense, right? So there are lots of things in our lives that actually only move in a line. And so when we talk about those things, we can use the one-dimensional linear reference frame to describe it. Okay, we have time to do one more, which is, I'll bet you can guess, the two-dimensional reference frame, right? Obviously. What would that mean? Let's think about it. A two-dimensional, or 2D, we sometimes just write 2D, but I'll write the word out. for now. What's a 2D reference frame? Well, this would be one where you had two choices, which would kind of mean four options. And generally, what you would get in a two-dimensional reference frame is kind of like two one-dimensional reference frames put together. So you could have north and south and east and west. So you have a north-south line and an east-west line, and if you put them together, you get a two-dimensional reference frame that looks like this. It could also be in and out, left and right, up and down, here and there, whatever. You could use any two sets together. Now, this takes on a whole new shape, because if you put these two together, you are now talking about this entire space. If you can go left and right and up and down, then you could go right and up and down and left. And basically this means that you could travel anywhere on here that you wanted. So this shape is more like a surface rather than a line. What do we call a shape like this in math? Sort of looks like a piece of paper. A plane? We call it a plane, right? So the shape of this is no longer a line. The shape of this is something called a plane. We say it's planar, or the shape is a plane, which is like a surface. It's kind of like a flat surface. We have to say flat, because you could have the surface of a ball, which is curved. That's not a plane. So a flat surface. There are lots of things in life that are on a flat surface. If you were up high in one of the press boxes looking at a hockey game on the ice, right? All these nice colors. Let's put in some lines here. There's blue lines there. With the nets down here. Okay, so we're going to play hockey. Well, I know that when the players bump into each other and they check, sometimes they lift off the ice a little bit. But you would notice that from way up high. Basically, you'd see all these players, and the players would be skating all around the ice. You'd never see a player jump way up off the ice, up into the air, and fall back down. That doesn't happen. This isn't figure skating. They don't do that. They just basically skate around on the ice everywhere. So you can see how this is exactly like this. The players move over the surface of the ice. And players can go either this way, say up and down. Well, generally in hockey we call this up and down the ice, right? And we call the blue line across the ice, or left and right. So it's a two-dimensional reference frame. My favorite example of a 2D reference frame is an old toy that looks something like this. It was a box shape. You'll remember this, I'm sure. And it had a big screen on it. Yeah, the Etch-a-Sketch. And it had two knobs, right? And of course, one of the knobs, if you turned it, moved up and down. So you turn the green knob, then you go up and down, and that's it. But if you turned this purple one, let's say, then the little line would go left and right. So each knob is like a one-dimensional reference frame. It makes a line. But if you turn the two of them together, then you could make the line go just about anywhere, all over the surface of the Etch-a-Sketch. So you've got one line up and down, the other line left and right. And what's interesting is that the two reference frames, the two lines you're combining, they combine at right angles to each other. That's kind of important. So a two-dimensional reference frame is two one-dimensional reference frames who are joined at right angles. Some of you are deciding to write that down. It's probably a good idea. Right? I won't write it here, but you can write it if you're taking notes. A two-dimensional reference frame is formed by taking two one-dimensional reference frames, or lines, joining them at right angles, and you get a plane. And one of the things we use in math all the time, like when I drew this, I thought some of you might just suddenly go, oh yeah, this looks very much like what we call a graph in math. It has a name. You know its name? It's named by the great French philosopher and mathematician René Descartes. Yeah, the Cartesian Plane. And this is a mathematical model that we can use to describe any kind of two-dimension. You could describe a hockey game using this. You could plot the players' positions with X's and Y's and where they move and how they go. And so we'll use that a little bit later on. So that's a 2D reference frame. Okay? All right, the next one would be the 3D reference frame. How would that work? Well, let's draw a line here, and let's talk about a three-dimensional reference frame. You're kind of getting the idea. You're just kind of adding lines together, right? So three-dimensional, there would be three choices to make. So you, in effect, would put three lines together. You have 6 options. So the easiest way to describe that would be up, down as one option, one choice, left and right as the other, and then forward and backward as the third. That's hard to draw on a board, but if we call this up and down, and this left and right, we'd have to imagine a line that was starting here and sticking out towards you, right? Sticking right out of the computer screen here, right out towards you. We generally draw it like that on a bit of a slant, but if you focus on that, it's like the corner of a room, right? If this is the floor down below, and that's the wall, you see how these lines are all at right angles to each other. It's 3 lines, all at right angles, right? And this, of course, is the 3D reference frame. This becomes more difficult because now the shape is not a plane. The shape takes on something called volume, right? In the last case, if we go back up here for a second, I should just mention this just because it's kind of neat. On all of these surfaces, you can calculate something called area, right? A line has no area, but 2 lines together on a flat surface, you can also do area. But that's it. Now we can introduce another concept called volume, because not only can we move, and I don't know if I can draw this, but not only can I move around here, but I could also jump out of the board and fill the entire 3D space. Right? So the only way I could describe that would be to draw this more like a cube than a right? So inside the cube we have this. And now you can buzz around inside the cube anywhere, inside the volume of this cube. And that would require 3 different choices you could make. Up and down, in and out, left and right. And that would be a 3D reference frame. This is the kind of reference frame we live our lives in, right? Because we have the ability to move in all these directions. Sometimes when we're playing hockey, we only move in 2. Or if we're trained on a track, we might only move in 1. But most of the time, people are free to move in all 3 dimensions. Makes sense. All right, the last one we could consider, you can keep adding dimensions, believe it or not. It's hard to visualize, but you can just keep adding dimensions by adding another line. Well, what would be the 4th dimension then? What would a 4-dimensional reference frame be all about? Because we could do that too. 4D. Well, I want you to imagine this. We actually do live in a 4D reference frame every day. We just don't realize that one of the directions or one of the dimensions is not a space dimension. It's a time dimension. So watch this. For a 3D reference frame, here you are in the school. You're up here in the corner on the 3rd floor in this little seat. Okay? If someone wanted to find you, they could use 3 dimensions to locate you in space. They could use a sort of a XY on the surface of the Earth, like your latitude and your longitude would tell us where to go on the surface, right? And then if you went to that latitude and that longitude, or that point, whatever it would be, it would put you, say, right here, but you must also indicate what floor you're on. So you have the up and downy part. So there's lefty-righty, or easty-westy, north and southy, and uppy-downy. And with those three things, you could find this particular spot in space precisely, right? But if you came to that spot at 4 in the morning, you might not find yourself there, because that's not when you are in that spot. So the fourth choice could be, when are you in that spot? So to actually find you right now in the universe, if you were going to tell your mother where to find you, you'd have to say, okay, Mom, I am at 30 degrees, well, what would you be? I think the Sioux is about 84 degrees west, I think, longitude. And then we're at about 46 degrees north, so that's our east-west. This is our north-south. We'd also have to say third floor, which is the uppy-downy part, which I can't really draw because it's in and out. And then we also have to say at to 30-ish, because that's the time element of when you're there. So you see there's 1, 2, 3, 4 different dimensions to locate you in space and in time. And that's about as far as we will go. However, you can go further, and you could have a 5 or 6 dimensional reference frame. And then you have to sort of wrap your brain around what that all means and how it would look. And it becomes very hard for humans because we're just so used to these 4 that anything else seems weird. But because we're using mathematical models, we can still construct a stage of 7 dimensions if we want. Just, we don't know how that would look, but we could do it. In fact, string theory, one of the things that's sort of on the cutting edge of physics today, suggests there might be 11 dimensions in total. So what numbers 7, 8, 9, or 5, 6, 7, 8, 9, 10, and 11 look like, well, you'd have to study a little more physics and a little more math before you could get a really good idea of how that would work. But you can kind of see the pattern. We won't go past 4D. So these are reference frames. These are the stages on which all of our scenarios will play out. Tomorrow we'll look at how we can represent these with math numbers instead of with words.